condition, we use a laser beam passing through the thin layer of soy sauce, and we can observe the thermal lens. And we were asked to investigate this phenomenon. Let us start with experimental setup. In order to control the thickness of soy sauce, we use the following. We took 2 glasses and put the thin plate with unknown thickness, and then we put soy sauce inside and clamped in these glasses. So now we can control the thickness of soy sauce. And in order to control the image, we did following. We use the laser. We control by inputting voltage, so the power was a constant, and the distance between soy sauce and the picture was 4 meters. 4 meters. We use only soy sauce horizontal because in first our observations we use vertically, and we saw some convection process. So our pictures was elongated. So therefore we use only horizontal soy sauce lens. And as for first observation, we can see with over the time the picture increases, then the picture decreases. And also we can observe the rings, as demonstrated on the slide. Now let's talk about qualitative explanation, why we can observe the diffusing lens. The slide demonstrated soy sauce and the 2 glasses. This is the beam. And our qualitative explanation is based on the fact that the laser beam hits the surface. So at this point we have the maximum temperature, and the temperature decreases with a distance. Next slide. Next slide. And due to thermal expansions, in the red point we have the maximum temperature, therefore we have the minimum density. And the density decreases with the increases with the distance. As we know the fact that the reflective index is proportional to the density, we can say that in the center we have the minimum reflective index. And the rays deflected the side with the bigger reflective index. So we have the dispersive lens. Next slide. And we saw that during the time picture increases and then decreases. And why we can observe it? After some time also source heated, and there are no temperature diffusing, therefore no changing of reflective index. Therefore we can observe that our lens didn't work. The time that our lens can be worked was 1 minute. Next slide. And why we can observe the rings? We got the screen and put some points on the screen. And if we summarize all illumination of all rings, we can observe the phase shift. The equation of the phase demonstrated on the slide. We can observe that the different point we have different reflective index and different distance. Therefore, we can observe the phase shift. And yes, correct. Now let's talk about mathematical model and talk about how the temperature in the soy sauce are changing with the distance. We write down the equation for changing the heat changes, and then write down how the intensity of the soy sauce changing during the time. The next slide. And to solve this equation, we must know the sum coefficient for the soy sauce. To find the absorption coefficient, we do the following. We use a Pascal light sensor and pour the different thickness of source source. This depends as demonstrated on the slide. Next. And we can observe this coefficient for source source that isn't a tabular value. Next slide. And we must know how the reflective index changes with the temperature. And to do it, we use the reflectometer. It is a device for measuring the reflective index of light. We got this dependence only experimentally, and we can find this coefficient. So now we can solve our equation and obtain how the temperature changes during the distance. And for better demonstration, we plot this dependence on the program, and it is the most important part of our work, how the temperature in the source changes with the distance. Next. And now let's talk how the intensity of the source changes on the distance. We know that the intensity is proportional to the amplitude. Next. Then we write down the phase if we know that in the focus all of rays are in one phase. Therefore, the phase shift doesn't depend on the radius. Okay, and now we got this equation. We plot this experimental theoretically and plot this dependence. And then we plot this dependence experimentally. This dependence using the light sensor that's demonstrated on the slide. We can observe some differences in our theory and our experimental. This difference can be explained following. First reason that our laser beam isn't round. Second, we have distance to the screen and length. In our mathematical model, we calculate that it is infinite, and our sensor has a size for smoothing the height. Next slide. And as we got a length, let's calculate what is the focal length. We write down how the reflective index changes with the temperature. Obtaining this value, temperature we got after our temperature distribution. Then we write down the phase shift, and obtained the next formula for theoretical calculation of the focus length of our source. This formula, and this is theoretical. How we can calculate it by experimental. Next slide. We can do following. Next slide. We put our laser beam and measure the radius of this beam. Then we put the source and see how this image changes. From the geometry, we obtained this relationship between this value, and we can find the focal length experimentally. And as for comparing our theory and practice, was for experiment we plot that it equals 20 centimeters, and as for theoretical, we obtained the same value. Let's talk about parametrical studies. We increase the current and see how our image on the screen changes with this. This experiment is next on the slide, and we the next. We obtained it on the graph. And how we can explain this dependence? We change the laser current. Therefore, we change the intensity in the source. Therefore, we change the temperature and the reflective index. If we change the reflective index, our rays have a bigger size. Therefore, we have the next dependence. Now we calculate how optical power of the thickness affects of the radius on the screen. We obtain this dependence, and how we got it. we took two glasses and played different number and put the different number of plate, and so we can control the height. Next slide. And using the refractometer, we observed how the density of the soy sauce changing with a temperature update this dependence. What was done in our work? Our experimental setup was constructed in the current. We can control the current. The next, we use only horizontal lens, therefore no convection process. Our qualitative explanation bases on the fact that a laser beam hits the surface and changing the density and changing the reflective index. Therefore, we have the dispersive lens. We discussed about reinformation. Therefore, we have a different phase shift in one point on the screen, and obtained how the temperature distribution on and the absorption coefficient. We got the theoretical formula for focal length and got the method for its measure for experimental. We find in coefficients showing how the temperature changes with how the reflective index changes with the temperature, and got comparing how the intensity changes with the distance with theory and practice. The dependence, we got the dependence image means from the laser current, and got the change in density with the temperature. And so, thank you for your attention.
Question from the opponent.
Alright, so you claim, so you claim that the density of the fluid decreases as you heat it. If that's the case, where does the fluid go?
Can you repeat?
If the density of the fluid decreases as you heat it, where does that fluid go?
If the density in the center changes,
and where does that fluid go?
come out,
Is it not sealed?
not sealed.
Is the soy sauce sealed within the two glass slides?
Can you repeat?
Is the soy sauce sealed within the two glass slides that you sandwiched it with? Okay, next. I'll move on. We can discuss it. So, do you assume that your beam is parallel as it passes through the lens?
What is the...
Do you assume the beam is parallel? Like, are the rays parallel?
Yes.
Do you assume the rays are parallel? Did you verify this?
Yes.
How?
It was our... We didn't measure it.
Okay, so you did not verify that it's parallel.
Yeah.
Alright, so did you consider the fact that, did you consider any effects of the absorptivity on the focal length? Like you calculated how some of the laser intensity light power is absorbed. So did you investigate those effects on the focal length? Yes or no? Okay. Also, so in your focal length equation, did you measure the beam radius? Sorry.
Yes. It equals using the in the screen we measure
the initial beam radius of the laser.
Yes.
How large is that?
We use can you open this slide? This one? Yes.
Not the spot, the laser itself. Like the radius of the laser itself.
We have lens diffusion and
Is the lens equation valid?
Sorry, there is no more time for an additional question. Please move on to preparation of the decision.
So let's quickly go over the problem statement again. So using a laser beam pass through a thin layer around 200 microns of soy sauce, the thermal lens effect can be observed. Investigate this phenomenon. So let's go through some of the tasks that we believe the court should go through. So first off, we must construct a very well-controlled experimental setup to very relevant parameters, as we are using lasers to control, and this verification of your experimental setup is very important. Second, we have to validate certainness. We have to look at into the Gaussian beam to actually analyze how the spot is going to form on the wall. Third, we have to derive a theoretical prediction for the focal length and the spot size, and fourth, we have to experimentally verify our theoretical prediction using our control experiment. Alright, so let's quickly go over a summary of the reform. So they have their experimental setup to control their soy sauce thickness, which we thought was appropriate using a spacer within two microscopes or glass slides. And then they had the quantitative theory and a qualitative explanation of the phenomenon, which I'll discuss more about later. And lastly, they had some experimental verification of their theory. So let's go over some of the merits. So they had their qualitative explanation of the theory, even though it was flawed. They talked about the density of the fluid. However, that is not entirely relevant due to the fact that the main reason why we see a variation in the density is just because of the thermal optic coefficient, which is dn dt, and then you can derive an equation for the focal length as a function of both that and the absorptivity coefficient, which the reporter failed. Second, they had their quantitative theory derivation with their lens equation, which again, as I'll talk about later, is not entirely correct. But let's go over some of the next steps the reporter could take. So first off, we believe there's a very limited theoretical model. For example, various assumptions were just simply not valid, such as the parallel beam. As laser, we know, is a Gaussian beam. There's only in the Rayleigh range, which is a small range, that's the only range where you might be able to assume that it's parallel. In addition, looking at the density change, as I said previously, that is not the main reason for this phenomenon. And also, we noticed in one of their equations, they did a first order approximation of e to the negative x squared or something similar to that, and that's going to introduce some errors in their theoretical predictions. Lastly, and finally, in terms of their experimental skill, there's no characterization of their laser beam. They did not measure the beam radius, which I'm not sure how they were going to calculate the focal length even with the lens equation from that, because you have to know the size of your initial object to be able to do that. And in this case, that again is not valid. And we just think there's not enough experimental control when you're using various optical components such as lasers, because that is very. So let's go over a quick overview of what we're going to be talking about in our discussion. So first off, I'd like to clarify the main origin of the thermal lens effect. So looking at absorptivity and why the index is changing. Second, we're going to go over some of the characteristics of the laser profile, as that was not very clear in the reporter's presentation. Third, we're going to go over some of the clarification of the theoretical assumptions that I talked about previously. And fourth, we'll go over some of the experimental improvements that I think the reporter could take to get some better results. All right, so I'd like to invite up the reporter to begin the discussion. Alright, so first off, I believe you said that density is the main reason for the density change, the main reason for the change in your index. Can you explain why you think that's the case?
Okay, let's show it slowly. We have a solar source lens and we have the laser beam.
Right.
In this point, the temperature is the maximum. Do you agree with it?
Yes, I do.
And we know that the temperature is proportional to the density.
Sure, but in this case, what would happen is after a very short period of time, you're going to have a distribution, such as so let's call this like your x-axis. You're going to have something similar. You're going to have a temperature distribution like this very quickly.
Right.
So initially, that's what's going to be occurring. And then this state will be achieved extremely quickly since you do have a steady T source. And a laser is I would assume it's fairly powerful. Although, did you measure the power of the laser to determine this temperature distribution?
Power of the laser equals 1 watt.
1 watt.
1 watt.
Okay. So could you again walk me through why you think the index is changing because of the density?
We have the temperature changes during the distance.
Yes.
And therefore we have the density changes with the distance. And the density of the solar source is proportional to the reflective index.
That's not entirely true. So in fact, what's actually happening is that you have, what we do have is you're going to have, n is going to, so n you can actually determine to be a function of n naught, so just assume, we assume it's not going to be, so you have 1 plus d n dt times delta t, right?
What is the...
dn dt is the thermal optic coefficient, which is a constant for a certain material, and this should be measured or taken from literature, depending on.
I agree with it. That I saw that this changing of the temperature depends changing of the density.
But here, as you can see in this equation, which is a known equation, there's no dependence on the actual physical density. It's only a dependence on this constant and the change in the temperature, which you can model with this distribution here, with this temperature distribution. Do you agree with this?
I agree with this, but why do you think that the density isn't?
The density, so what happens is since you're sealing, so you're assuming that the volume is going to change.
Yes.
And the volume is.
Volume changes.
Yes, however, as you said in your experimental study, you essentially sealed your soy sauce within a very small container, right? You essentially sealed it.
And the soy sauce goes
As such,
inside.
within this sample, right? It's sealed. There's like a barrier here to prevent it
We
from
use
leaking
our
out.
thermal lens croissant.
Yeah, but that doesn't make a big difference.
Okay.
So it's going to be sealed. So it's going to be sealed inside here. So I don't think the volume is going to be changing. And
Our experiment will changing.
why? Because you
Because
said you sealed
there
it.
is changing of the temperature.
Right, but the volume is not going to change very significantly, and again, the most important, that is completely negligible if you compare it to actually this here. So if you want to, you're saying essentially it's going to act, the soy sauce is going to turn into this sort of a shape to create a diverging lens. However, so even with the volume argument, there's a flaw in that because if you assume that the volume is increasing, you'd actually produce a lens of this shape, which is you produce a lens of this shape, which is clearly a convex lens. So you'd actually get a focusing beam. So that's another flaw in your theory, right?
In our theory,
Do you not agree?
I want to say that the reflective index depends on the temperature. Yes, it's right.
But
And
not on the
there's-
density. Not on the density changing or the
in
volume.
our experiment changes the density, changes the volume. Therefore, we have this dependence.
Right, but as I
Can
said,
you prove that the density?
yes, because in your experiment, it's not
In
changing.
our experiment, we use horizontal and
Yeah, but even if it's horizontal,
the soy
right?
sauce
what happens
goes
is
inside.
that then the soy sauce could leak out and you have much greater problems in your experiment, do you not? Like you have your soy sauce here, right? Then your soy sauce is going to leak out
yes.
if it expands. Is that what's happening? So your volume is that what you observe?
Yes.
Then how do you measure this volume change?
We didn't measure this qualitative explanation.
But that's a huge part of the theory if you're going to make this assumption, which I do not believe is valid. Okay, anyway, so let's move on. So let's move on from this temperature. So as we know, so you have the characterization of your laser. You assume that it was a parallel beam. Why? You cannot actually assume that, since as we know, laser beams actually have a gasoline profile. So something similar, something like this. Where here, this is known as this is like your beam waist, which is to be indicated by W naught. So that's what a laser actually looks like. Obviously, this is not to scale, but in this scenario, you cannot actually assume that your laser beam is your laser is going to be parallel at the lens, because in that case, if it is parallel, as you know, this temperature distribution is going to be symmetrical. So you're not actually going to see a spot if you make this assumption. If you assume it's going to be parallel, you're not going to see a spot. You're just going straight through. You're going perpendicularly through essentially glass. So why would you won't see any change in spot size?
It's our assumption that the laser beam
Yes, but if you assume it's parallel, and if you assume it's parallel, and we accept the fact that this temperature distribution is true, and that the index varies with the temperature distribution, what's going to happen is, since can I assume that your laser passes through the center of the soy sauce sample, or the temperature distribution will adjust appropriately. So in that scenario, what's going to happen is the index here is going to be the same as the index here, so it's going to be symmetrical. Am I correct? The index at let's draw like gymnastics, right? So let's say at this point, so right, so this is going to be symmetrical about this point here. So let's call this like x1 and x2. So at x1 and x2.
Coordinates, yes?
Yeah, so at x1 and x2, right, you're going to expect, according to that temperature distribution, according to this equation, you would expect the index to be the same.
Yes.
So in that case, the beam would just pass through. You would not expect to see any divergence in that scenario. as in you would not see this sort of diverging effect at your.
It is our assumption that
But you cannot make that assumption because in that scenario, what happens is that there will essentially it'll just pass straight through. What you actually have to assume to solve this problem is you actually have to characterize the Gaussian beam and find, like essentially you have to find, like you're most likely not going to be in the range. So this is known as the Rayleigh range, and that's the range where you can make a valid assumption of a parallel beam. However, unless you determine what that range is and that you're conducting your experiment in that range, you cannot make the assumption that your beam is parallel. And also this phenomenon will not, as I explained, will not actually occur in that range. What we actually have to do is you have to find essentially your phenomenon is going to be occurring somewhere after that Rayleigh range, and that's when you're going to see that phenomenon occur. Right? Does that make sense?
How we can work that our laser beam will be parallel?
Right, your laser beam is not parallel. Lasers are not, like, they're much better than your standard like flashlight or something. However, if we compare, a laser, in this experiment, we must still verify that this is not parallel, and that's an invalid assumption. Do you agree? Would you agree with that?
I agree with that the direction of the laser beam depends on the temperature distribution.
Okay, so we can actually, so what we can do, so do you think do you have a way of solving for this, just how B would diverge? Can you solve this? Do you have a method? Since I think we've proven that the beam is not in fact parallel, can you think of a way to characterize this laser beam, to gain this kind of a function? So this is going to be like some z-axis, so the direction of propagation, and this is going to be your width. Like, this is going to be like the radius of. So this is the radius of your.
Do you want to depend?
No, like how would you construct? Could you construct an experiment to characterize this beam? So you can write. So for a Gaussian beam, you can write it as I is equal to I naught as a function of e to the negative r squared over. So this is the yes. So you can characterize it as this, right?
The intensity of the source change.
Right. So this is so you can do this, right? So but can you think of like an experimental setup where you can actually solve and characterize your laser? Because that's an extremely important part of this problem that I think you failed to address. Anyway, so moving on, can you clarify some? So actually returning back to the thermal lens. So, so how do you think, actually when you do this experiment, what happens is you must actually add a converging lens before, so let's assume this is your soy sauce sample, and you actually must add a converging lens. Normally you must add a converging lens before this to essentially amplify the effect of the divergence. So, would you agree with this? Okay. So in that case, how would you actually represent?
Sorry to interrupt you here. May I ask you to please summarize the discussion?
So I think as a whole, we were able to determine some of the flaws of the reporter's theory. For example, the fact that they assumed that the density change was responsible for this phenomenon, I believe is inherently flawed. And we discussed how we might be able to model this using the temperature distribution and this equation of n is equal to n naught times 1 plus Tn over Tt times delta T. And from that, we might be able to derive some representation of the focal length. In addition, as I stated previously, another important task of this problem was describing the Gaussian beam. And what I believe that, as we discussed, we can employ several methods, such as using a laser beam, or if we can get a laser profile to characterize the Gaussian beam. Then using the Gaussian beam, we were actually able, and several other equations, we will be able to predict the spot size on the wall, which I believe the reporter was not able to do in the presentation. Just as a
Okay. Thank you. 3 minutes time for the reviewing team to pose questions to the opponent as well as the reporter.
Okay, so hello, my name is Filipino. I'm going to review this task. So first, the question for both of you, a quick answer. What did you measure the time velocity of your crystals, or is the thermal lens effect?
What you measure?
The time development, because I can imagine that you just place the lens of the sample right in front of the laser, it wouldn't create a thermal effect like it. So have you measured somehow what's the time dependence of the formation of the thermal effect?
In our experiments, we let the thermal lens work about 1 minute.
Okay, so what do you think if
The
it's
thermal,
too
so
long or if it's
reaching
too short?
reaching the steady state as I like so like heating it up and getting that temperature distribution, right?
Okay, so nice question. What do you think about the placement of the source cells? You stated that you in your experiments you said that you have parallel arrays. So what do you think that the placement will change it?
If we change not parallel, we have the another temperature distribution.
No, I'm asking about if you assume parallel arrays, would it depend, would the effect depend on the placement of the soy cells, of the sample in front of the laser? Okay. For both of you, does this effect depend on does this creation of the thermal lens effect depend on the gradient of the temperature or the change in temperature?
Gradient.
On the temperature or the gradient.
Or the gradient.
Well, it depends on this temperature distribution as I've shown here. So yes,
so
in that
the
sense,
gradient, so the
both.
gradient.
But you need the temperature difference to see the in the index.
Okay, I'll ask the opponent.
Yeah.
Why do you think that you have to place, again, because I thought that you didn't say it correctly, but why do you think that you have to place the converging lens in one of your
So just on its own, these soy sauce lens is not going to, first off, your laser beam is extremely small, right? In general, your laser beam is going to be small. So to amplify this, we add a focusing beam, and then we place the soy sauce. So for my experiment, I place the soy sauce approximately at
When you don't. Okay, so you place it. Oh.
And what that does is it amplifies essentially the temperature at the point where the laser hit is much higher, and you see a much greater effect. And then, we measure the spot size.
But you want to see when we look at the Gaussian profiles, you stated that it looks like a Gaussian profile.
Yeah, so I was just saying for the Gaussian profile that you can't actually make that parallel assumption without verifying it. And the parallel assumption is only valid for this radius range.
Okay,
but in my experiment, I did not actually.
How did you measure that the radius is they used to parallel arrays, and how did you measure that the radius is same and then assume that it's parallel arrays?
How we measure radius of the arrays?
Okay, thank you. Today's time for preparation of the review.
Slovakia, and I'm going to review this task number 8, soy sauce optics. So I don't think we are all familiar with the soy sauce optics. So we can skip this. First, to the summary of the report. They introduced us their experimental setup with their ability to control the thickness. They have the control calculator, and also they ensure that the sample isn't leaky. Then, to the phenomenal explanation, they try to qualitatively explain how the effect is how the temperature is changing over the dimensions of the width of the soy sauce and the soy sauce. Okay, and then the theory was based on the equations and the diffractions. Then to the experiments, they tried to investigate the intensity profile and the focal. So to the report generally, their experimental setup we find quite good, but they didn't ensure that how they look the propagation of their laser. They based their theory on heat equations, as I stated. Then they had correlation between an intensity profile, but on the graph we didn't see any units or anything that was really saying anything. Then we didn't get a quite clear explanation of the refractive index gradient. And next big mistake for the was that they didn't account for the heat flux in glass. Next to the opponent, they tried to attempted to explain this phenomenon more clearly. They picked up the point that the beam parallel assumption isn't right. Then they said that they asked about the experimental setup, but what we missed was the lack of the time dependence involvement of the thermal effect, because this is the real thing that what the task asked us to do is to investigate the thermal lens effect. And to the discussion summary, they were talking about the thermal lens effect and reporter was talking about the inverse proportionality to temperature. Then they also talked about the importance of the Gaussian mean propagation, which we agree with the opponents. They talk about also the theoretical assumptions and their experimental proof. So the clashes were the importance of density, as the reporter stated, that the opponent says it's dependent on the thermal coefficient, and we agree with the opponent that this is the gradient of the temperature which is important. Another clash was that the laser was parallel, and because the opponent said that it can't be parallel, and we also agree with this that the Gaussian universal is important in this effect. Also, they had a clash with the spread of the laser, which we agree with the opponent that the specific curvature of the propagating beams is evolving such a hyperbolic functions as he drew on pictures. But then I didn't like about the opponents that he presented more of his own experiments and talk about not talking about there.
Okay. Sorry to interrupt you.
Yeah.
2 minutes
Thank
time
you for
for
your attention.
2 minutes time for concluding about 5 and 4.
During the discussion with the opening, we discussed about quality explanations. I saw that the main reason of the thermal soy sauce length is the changing the temperature with the distance, and the density changes too. We have the graph shows this dependence, and in our experiment, some parts of soy sauce go out, therefore proves that the density changes. And this coefficient changes the density during the temperature. This graph shows how the density changes with the temperature. And in our experiment, we use that the laser beam was parallel. Of course, the distance between laser and the lens was 10 centimeters, and it is right. Our assumptions. Thank you for your attention.
Okay, thank you. I guess there's some time for 30 questions. Yes,
Reporter, could you show us the slide with the temperature profile? Special profile that you use in your theoretical model. Theoretical temperature profile, R squares minus R squared. So you solve some problem, of course. Yes. So the coefficient, the thermal coefficient, kappa. Where did you get this? Is it fitting parameter, or you get this?
We use this parameter. We calculate this parameter as for water.
For water.
For water.
What about? So you input it. You put it into your.
Yes.
And you get this. We consider this comparison with your experimental data.
We can't measure it. Therefore, we use like water.
So you didn't use this parameter fit. Okay.
Any more questions? If not, I would like to pose a question to the reporter. The task specifically specifies 200 micrometers as sufficient spacing. May I ask you, how is spacing controlled in your experiments?
How we control?
Yeah, how is it controlled?
We control.
Yeah, like you mentioned. Sorry, you mentioned this. You have spacing plates.
Yes.
How do you make them?
How we? We know the thickness of the plate, and we
Could you tell me what kind of plates are those? I still don't get it. Sorry.
We have a thin plate and clamping the glass. Therefore, we have one thickness. We clamping.
Yeah. What's in between? Sorry for. What's in between the glasses? What's the material?
Material.
It's like a thick.
Aluminium.
Aluminum. Okay.
Aluminum.
Okay. Additional questions? Okay. If not, I have a question for the opponent. You mentioned that conducting the experiment, the overall observation might differ from the case where actually the soy sauce is sealed and not sealed.
Right.
Can you elaborate on that a little bit?
So
what would actually change?
I was trying to clarify because I assumed that it was sealed, but I guess with aluminum it's not going to be perfectly sealed. So in my scenario, what I want to use is density for my experiment was not an important factor since I used a Teflon spacer in between two microscope slides. And then then I would assume it's sealed, and then I guess there's minimal expand. And then I filled it up, and then I filled up the space between, and then I, like with a dropper, and then I clamped them together.
Okay, I understand. Okay. Yes.
To the opponent, you stated that you write down this formula for the change on the refractive indices. Of course, it depends on the density, both on the density and on the temperature, because of the thermodynamic state. So what is the derivative? Under the constant density, or it's partial derivative, or it's?
So this is just a constant for.
I mean, it's a partial derivative under the constant density, or what kind of derivative? Because the refraction.
So you would assume that it's constant density, yes.
Constant density. So
yes.
you take into account all the thermal dependence of the refractive indices.
For this experiment, yeah. So this TFUT is the main one.
To the reviewer,
I think it's a partial differentiation of the.
So the main cause of the effect because of the thermal dependence of the refractive index.
Yes, and I think.
Not the density dependence.
I think it's the.
Do you agree with that?
Yes.
The main reasons change temperature.
Okay. Question to the reviewing team. You mentioned that the reporter was controlling convection. Could you explain what the background of that statement was?
I think it was with the placement of the soy sauce, and it was with that she did
The sample was placed horizontally,
Yes.
and therefore it could not flow.
So convection is an issue.
with her experimental setup, yes.
Okay. Yeah, I'm sorry. Time's up. So, and there's no more time to do questions. And we'll move on more. If you were more following the report actually, then leading the discussion with your own idea. I mean, there were a lot of experimental weaknesses inside the report, which I would have liked to see it discussed. But so that's why 6 is still an over average opposition. But yeah, it wasn't really structured as long as the report. And normally the opposition is supposed to answer to the report and to respond to the report rather than following an own idea. On the review, 2 low 4s by me and Vladimir. Yeah, I felt like the reviewer didn't bring any new aspects to the discussion. There was one aspect you brought, let's see, which was the time dependence, which was your strongest point, I believe. Because I also believe that time dependence is relevant when actually looking at the experiment, because one of the reporter slides was named, okay, after some time we see that. So I would have like you, and you asked also for a characteristic time in your question stage, and I would have like you to see, or to see a discussion on that, how the time dependence would actually, how you would expect the time dependence to happen, and what a typical time scale would be. I mean, the task clearly states 200 micrometers, so it should be possible to give a discrete estimation of the time dependence. So if you're asking for it, I would like to see an answer from you. So, despite that, I think the review had strengths and weaknesses, which somehow cancel off.